At precisely 10:23 p.m. last night, a network of instruments embedded deep in the Pacific seafloor detected a shift that was not supposed to occur for at least another year. Far below the surface, hidden beneath nearly a mile of black, crushing ocean water, the summit of Axial Seamount had expanded to a critical point. Measurements showed the volcano had reached 95% inflation, the exact danger threshold that preceded its 2015 eruption. But the timeline scientists have been counting on has suddenly collapsed. What was once expected to unfold gradually through late 2026 is now accelerating at an alarming pace. Magma pressure beneath the ocean floor is rising faster than ever recorded. A slow, predictable build-up toward eruption has transformed into a rapid race toward geological instability. And while this volcano remains invisible from the surface, its next move could unleash effect capable of reshaping the Pacific coastline itself. The most unsettling reality is that Axial Seamount does not exist in isolation. It is a central component of the Juan de Fuca Ridge system, the same deep tectonic engine that feeds the Cascade Range. From Mount Baker in the north to Mount Shasta in the south, every major volcano in the Pacific Northwest draws magma from this shared underground network. When Axial finally ruptures, the energy released may not stay contained. Instead, it could surge through interconnected magma pathways like electricity racing through a circuit. So what happens when the most closely monitored underwater volcano on Earth reaches its breaking point months ahead of schedule? Why are the very scientists who successfully predicted its last eruption now admitting the timeline no longer makes sense? And if the geological foundation of the Pacific Northwest is more interconnected than once believed, what other disasters could be triggered by a single submarine eruption? Roughly 300 miles off the coast of Oregon lies a volcanic mountain few Americans have ever heard of, yet it ranks among the most active and potentially dangerous volcanoes in North America. Axial Seamount rises nearly 3,600 feet above the ocean floor, its summit still hidden beneath an immense column of Pacific water. This is not just another submerged ridge or seafloor bump. It is a massive volcanic structure directly linked to the same magmatic system that fuels the Cascade volcanoes on land. Unlike the towering stratovolcanoes of the mainland, Axial sits directly atop the Juan de Fuca Ridge, a spreading center where tectonic plates slowly pull apart and new oceanic crust is born. Here, magma continuously rises from the Earth's mantle, feeding a colossal volcanic edifice comparable in size to Mount Rainier. Axial does not erupt sporadically and then lie dormant. Instead, it inflates and deflates rhythmically, like a gigantic underground lung, drawing molten rock inward and releasing it on a semi-regular schedule. Dr. Bill Chadwick, a geologist at Oregon State University who has studied Axial for decades, describes the process clearly. Historically, the volcano inflates to nearly the same level each time before erupting. That consistency allowed Chadwick and his team to accurately forecast Axial's 2015 eruption. But that predictability has now vanished. Inflation that once took many years is now occurring in a matter of months. Magma is surging upward. The established cycle is breaking apart. On July 29, 2025, a massive magnitude 8.8 earthquake struck near Russia's Kamchatka Peninsula, sending seismic waves racing across the Pacific Basin at jetliner speeds. Thousands of miles away, those waves converged on Axial Seamount. Pressure sensors buried in the seafloor registered the disturbance even through nearly a mile of water. Within hours, earthquakes rippled through Axial's magma chamber. Inflation rates doubled, then tripled. Months later, in November 2025, another shock arrived. This time, a magnitude 7.9 earthquake rocked the Tonga Trench, more than 2,400 miles to the south. The resulting tsunami swept across the South Pacific, while seismic waves once again hammered Axial from below. Fresh lava spilled onto the seafloor, but this eruption was only a warning sign. By the end of the month, Axial's inflation rate had quadrupled. What should have taken a year was now unfolding in mere weeks. The final blow came even closer. On December 8th, a powerful earthquake swarm erupted along the Blanco Fracture Zone, a major fault slicing across the Juan de Fuca Ridge just 60 miles from Axial. Instruments on the volcano's summit recorded more than 2,000 earthquakes in a single day, with at least a dozen reaching magnitude 4.0. The effect was like repeated hammer strikes on an already fractured structure, completely shattering the long-established eruption pattern. By December 20th, Axial's inflation surpassed 95%, the same level that triggered a major eruption in 2015. This time, however, it occurred 10 months earlier than expected. To understand why this acceleration is so deeply troubling, we need to look back nearly a century. In May 1933, a U.S. Navy subchaser patrolling off the Oregon coast recorded an unusual entry in its ship's log. The crew reported being awakened at 5 a.m. by a strange light and discovering pieces of volcanic rock floating at the surface, emitting gas bubbles. That forgotten log entry, buried for decades in naval archives, is now recognized as the first documented eruption of Axial Seamount. Scientists believe the 1933 event involved submarine lava flows that spread across the seafloor, creating a massive underwater plateau larger than the city of San Francisco. Yet the true scale of Axial's power remained hidden until July 1998, when seafloor seismometers detected an enormous seismic swarm. More than 8,000 earthquakes shook the volcano over just 11 days, some strong enough to be detected by monitoring stations as far inland as Idaho. When remotely operated vehicles later surveyed the site, they found lava flows stretching up to 10 miles across the seabed. The pattern repeated in April 2011. After 13 years of steady inflation, Axial erupted again, producing earthquakes up to magnitude 4.7. Monitoring equipment captured lava pouring from multiple vents, building new volcanic mounds rising 300 feet above the seafloor. These flows covered an area 3 times larger than those from 1998. Then came 2015. On April 23rd, Axial's inflation reached a critical threshold, prompting scientists to issue a rare warning that an eruption was imminent. The next day, a magnitude 5.2 earthquake struck, followed by sudden silence as lava severed underwater communication cables. The volcano's conduit had reopened, flooding the abyss with molten rock. For decades, each eruption followed a clear pattern: 13 to 15 years of gradual inflation, then rupture. Now that pattern no longer holds. The eruption cycle has compressed from decades into months. The only force capable of accelerating geological processes on this scale is Axial's increasing entanglement with seismic activity across the Pacific Basin. Why is this happening now? The answer may lie deep within Axial structural roots. Beneath the volcano spreads an intricate web of dikes and sills, magma-filled fractures that can extend for miles through the oceanic crust. These conduits do not merely supply Axial, they connect it to the broader Juan de Fuca Ridge system. When Axial erupts, it is not just releasing pressure from its own magma chamber, it is drawing from a vast, interconnected reservoir feeding volcanoes throughout the Pacific Northwest. When a major earthquake strikes near one of these magma pathways, the shaking can clear mineral blockages, suddenly allowing trapped magma to surge upward. Axial's inflation then becomes driven not only by local magma buildup, but by high-pressure injections from the entire network. Scientists believe this is exactly what occurred in 2025. The Kamchatka quake, the Tonga rupture, the Blanco fracture zone swarm. Each event battered Axial's subsurface plumbing, clearing bottlenecks and mobilizing magma far beyond the seamount itself. Axial is no longer inflating on its own. It is being force-fed by seismic stress transmitted across the Pacific. The consequences could be profound. If Axial erupts on this accelerated timeline, it may not simply alter a section of seafloor. It could destabilize the Cascadia subduction zone, a 600-mile fault capable of producing magnitude 9 megaquakes. Dr. William Wilcock, a geophysicist at the University of Washington, outlines a chilling possibility. Axial's eruption could trigger earthquakes along the subduction zone by altering stress conditions and fluid pressures deep within the fault. Picture the chain reaction. Axial's dikes rupture. Shock waves propagate through the Juan de Fuca plate's brittle crust, weakening an already strained fault system. The subduction interface could fail catastrophically, unleashing a magnitude 9.3 earthquake that devastates the Pacific coast from California to British Columbia. Cascade volcanoes, already primed by shared magma connections, could erupt in a cascading sequence. This is not speculation. It mirrors ancient patterns preserved in the geological record. Sediment cores from the Pacific seafloor reveal layers of volcanic ash and turbidity deposits, evidence of underwater landslides triggered by massive earthquakes. These layers repeat rhythmically over the past 10,000 years, suggesting that the catastrophe unfolding at Axial may be part of a long-standing geological cycle. Now that cycle is accelerating. What once took centuries is happening in months. The Pacific Northwest magmatic system appears wired for disaster, and the volcano most capable of igniting it sits alone on the abyssal plain, 300 miles from the land it threatens to reshape forever. The most heavily instrumented volcano on Earth is sending a warning signal. Are we listening? Will Axial's premature eruptions remain hidden beneath the waves? Or will they shatter the Pacific Northwest as we know it? Share your thoughts below and subscribe, because we may be just one breaking point away from the defining geological story of the century.